So we can now move to the next topic in our course. We are actually in overall Unit 6, which are new predictions of our new theory. And we've completed now our discussion of scattering states, at least for the meanwhile. We might have some time later in the semester to come back and look at some other interesting scattering phenomena, but we have now a pretty complete understanding of that theory. And now we can move to a new topic entirely, which is the bound state theory, the theory of bound states. Now, what I mean by bound states specifically is that my particle is bound. It's kind of tied down to a particular region of space. For something like that to occur, I would need my potential to have the following type of behavior. Here's v of x as a function of x. And my potential, who knows, it might have some different bumps and things in it. But what has to happen to keep my particle, when it has energy E, localized to a particular region of space is I need to ensure that the particle can't escape from this region. That means I must have classically forbidden regions far out towards infinity and minus infinity. So the condition for bound states is that I need the energy to be less than the potential at minus infinity, and I need the energy to also be less than the potential out at plus infinity. If I do that, then I will have these forbidden regions far out here, and you can imagine physically then what my particle must be doing. It's going to, if it ever does go into one of those regions, and we know from tunneling that's entirely a possibility, it will eventually be expelled by that region and put back into the classically allowed region. And so it will in general have some kind of orbital period in here. Right now I am speaking semi-formally, but this helps us understand what's going on. So if that would then immediately tell me that I expect there to be some energy spacing between my energy levels that goes like Planck's constant divided by the classical period of this motion, or at least approximately so. And because my particle is now bound to a finite region of space and has a fixed amount of energy, that time is going to be some finite number. It's no longer an infinite number, right? If I don't have a bound state, my particle can tunnel out and then escape towards infinity, and it's never going to come back, which would give me an infinite classical period, which would then give me no spacing between my energy levels. I would then have a continuous distribution of energies. But in the bound state case, and we were going to see this in some detail coming up more formally, but in the bound state case, because there's a finite orbital period, not infinite, that means the energy spacing I can expect to be some non-zero number. So I'm expecting then to have discrete energies when I talk about bound states. Now, when I have discrete energies, that changes things a little bit for me. One of the most important things we have in quantum mechanics, as you guys know, for instance, how we solve the time-dependent Schrödinger equation, is the energy representation. But the energy representation now is going to take on a somewhat different flavor because of the discreteness of my energy levels. So before we begin actually solving detailed problems with bound states, it's useful for us to actually begin to consider in some detail what the energy representation looks like in the discrete case. So let's go back to basics here a little bit. So I want to look at energy representation. And in particular, I'm looking at this discrete case. Now, for the discrete case, what I am saying is that I can, of course, use quantum principle of superposition. And the idea then is that any arbitrary wave function, psi of x, and notice I'm not talking about dynamics or time evolution, just some quantum state at some particular point in time, can be expressed then in terms of a superposition of the pure states of energy that I would get, right, that would come out as the result of a measurement of the energy of the system. So those pure energy states I will call phi sub n of x. So these are my pure states of E. And the energy values that go with phi sub n, I'm going to call E sub n. So these are pure states of energy, E equals E sub n. We know how to get them from the time-independent Schrodinger equation, right? Those would be solutions, so those come from the time-independent Schrodinger equation, which will tell me that the Hamiltonian acting on each of these states, of course, gives me that state back again. But what I'm trying to emphasize in terms of a representation is I can represent any wave function as a superposition of these. Now notice that because they are discrete now, right, it's a discrete sum over those. It's no longer an integral. And then the weights in the sum I can call W sub n. Now to understand a little better and to keep our intuition going about what this means and how we might be able to manipulate it and the questions it can help us answer, I'd like to put on this side of my screen, I want to try to split it about down the middle. On this side, I want to put down a more familiar representation, some continuous representation. And so we might want to think about, for example, the momentum representation. That's something we're very used to. Representation. And for momentum representation, it's a very similar statement, except of course now it's a continuum. So there we had an integral over all wave vectors k of some weights, and we called those weights psi tilde of k. And then that multiplied my pure states of momentum, which were properly normalized, e to the I kx over the square root of 2 pi. And I hope you can see this looks very much like this form of the superposition. The two slight differences, or really it's just notation, is this then represents my pure states of momentum. And the factors that are multiplying them before I add them up or integrate them, this is then the momentum representation of my wave function. So these WNs, this list of discrete numbers now, not a function, but this list of discrete numbers now, make up the energy representation of my wave function psi of x, just like the psi tilde is the momentum representation of my wave function psi of x. Okay, good. So that's the first difference, that we will have now discrete sums instead of continuous integrals. One last little technical note I want to make, but I don't want to emphasize this too much because I really want to focus on the discreteness of the sum. You'll notice, though, that sometimes if I increase my energy enough, I will get to a point where the energy of my particle exceeds the potential out on one side or another, and suddenly I will go from where I have discrete energy levels to where I have continuous energy levels. I would then have to supplement this sum with some kind of an integral. I'll just draw it in my usual notation with the integral sign, but I'm just going to do a slightly dashed version to remind you I'm not focusing on that case right now. Right now, let's just imagine I only have discrete energy levels and focus on those things that are particular to that particular case. Okay, so once I have this quantum principle of superposition, here are some of the things that we're going to be able to do with it once we actually know how to solve for these bound state wave functions. One of the most primal questions we can ask is, if we do a measurement, when we measure the energy, E, we find, right, of course, just these allowed values, En, but with what probability? With the probability of E sub n should equal what? Well, if we're at all rusty about what that should be, we can simply look at our momentum representation that we're very familiar with. You will remember that if we measure momentum, the probability of getting any momentum is just literally the square of the associated representation of the associated weights, modulo squared, from my superposition. So I would expect this probability should be directly related to the modulo squared of my weights. And if you remember Dirac's statement, it should be somehow related to those, proportional to them maybe, one of the big questions we will have to address if we make a good, proper representation of things, hopefully we'll carry things out nicely so that alpha will actually equal 1. And so I shouldn't really leave this as a question. This is really my result. The main question is alpha going to be 1? How can we do things properly? Now, this is great. I know how to get the probabilities, but the big question is, okay, I can get the probabilities from the weights, but actually, how would I get the weights? To get the weights, okay, or I should say where, right? Just follow my train of thought. Where the weights are. So there should be some mathematical procedure I can follow to get my weights, some mathematical procedure to compute them from my wave function. Right? If this W is really some equivalent representation, this collection of these coefficients, well then I should be able to convert between them. This shows me how to go from my collection of coefficients to my wave function. I should be able to go in the other direction and get my weights or my energy representation from that wave function. Now, again, to draw inspiration of how we might calculate this, we can always ask ourselves what was the behavior that we saw in the momentum representation. So in the momentum representation, the way we got the weights there was in order to compute the momentum representation of my wave function. I hope you remember the way we did that was actually to invert the Fourier transform. We use the inverse Fourier transform theorem, which looks like this. We integrated dx, my wave function psi of x, times an e to the minus ikx now, so that it does the inverse Fourier transform, and it carried this normalization 1 over root 2 pi. We had decided to do the Fourier inversion theorem. We had spread these square roots out evenly. And one of the key reasons why we did that actually is that I hope you can recognize in this formula that what I have here is nothing other than my pure state of momentum, but complex conjugated, which would then just flip the sign on I. The beauty of this, though, I hope you'll recognize, is this has a very nice compact notation because this is just a Hermitian inner product. So to get the weights in my representation, or to transform my representations, what I do here is I take the inner product of my pure momentum state with my wave function. So it stands to reason then that, well, and this now is a bit of a guess we will have to prove, but we're hoping we can get these weights by taking the inner product of my pure states of energy, my phi n now, instead of my phi k, with their wave function. Now, to prove this, we need a certain fact. And to figure out what we need to prove that, we can go back to actually what it was that helped us prove the inverse Fourier transform theorem. Right? So the inverse Fourier theorem we proved, right, the inverse Fourier theorem. In the middle of that proof, there was one key result that we used over and over again that we needed. It's the key fact that enters any proof with Fourier transforms, and that is this following integral. If I have an integral over dx, we had e to the minus ikx over the square root of 2 pi, multiplying e to the I plus I with a different k prime x over the square root of 2 pi. And you might recall what that gave us. To remind you, I could write it this way. Integral dx over 2 pi of e to the ix, or minus ix, k minus k prime. And hopefully you will recognize that that is just the Dirac delta function of k minus k prime. That's what we always use in our Fourier proofs. I want to get us more and more used to the Bra-Ket notation, and notice that this also has a very nice interpretation that way, because once again, this is phi k star, and this term then is just phi k prime. So what we used actually for our proof was that the inner product of any two different pure states of momentum gave me the Dirac delta function. Now, this then leads us to think that the key fact that we need over here somehow relates the inner product of one of my pure states of energy, say phi n, with another of my pure states of energy, phi m. And the result of that overlap actually has two different cases. First, we have the case where n is unequal to m. And you all actually proved, it turns out, on a problem set that our states have to be what are known as orthogonal. They have to be, their inner product has to be 0. We call it orthogonal because, remember, inner product is like a dot product, and when the dot product of two vectors is 0, that means they are at 90 degrees or orthogonal. So we get 0 in that case, and that was something that we proved on a problem set. In the case that n equals m, that's kind of interesting, right? That would give me the inner product of phi n with phi n, which, if I write it out, is the integral over x of the magnitude of phi n of x squared, which just represents, of course, the total probability that when I get one of my pure states of energy after doing my first measurement, the total probability of finding the particle in that state somewhere. And that probability, of course, always adds up to 1. So I get 1 in the case that n equals m. And this quantity comes up very often in these proofs, so it's very useful to give it a symbol or a name. And because of the close analog between what I'm finding here and the Dirac delta function, this is also called a delta function, delta, and it's a function of n and m. But it's a different type of delta function. It's kind of a discrete version of the delta function, so it actually has a different name. This is called the Kronecker delta function. And it is defined precisely according to this definition. And so we can compactly write down the overlap of any of our two states. The last comment I'd like to make is really how analogous this is to the Dirac delta, right? The Dirac delta gives me 0 unless k equals k prime, just like this gives me 0 unless n equals m. Also, Dirac delta gives me, of course, a big peak when they are equal, but the peak is designed so that the integral under the peak is just 1, just like this peak is designed so that the sum under this peak is just 1. And the terms under the peak are all zeros except for one term, so this indeed will sum to 1. So this is actually the direct analog. Great. So where we will pick up in our next set of discussions is, once we know this fact, what we want to do then is to finally prove and convince ourselves that this is how we can extract the weights. And once we have the weights, we then can begin to consider finally whether this probability formula works and whether it's a rational formula.